between a currency and a domain name system. So one of those is both systems involve economically valuable assets. So in Bitcoin, there's an economically valuable asset called a Bitcoin, which you can transfer around. In Namecoin, the economically valuable assets are, well, domains. If you manage to register, say, bitcoin.bit back in 2010, you can probably sell that domain for quite a bit of money now. And even on the internet, if you manage to register something like abc.com back in 1995, you would be rich now. I don't even know for what price a domain like circle.com sold for. So the other big similarity between currency and Namecoin is it's a system where it's very crucial to determine which transaction came first. So for example, if I have $100 and I make a transaction sending those, or if I have 100 Bitcoins and I make a transaction sending those 100 Bitcoins to you, and then I make another transaction sending those 100 Bitcoins to someone else, obviously, and then I publish both of them, obviously both of those transactions can't make it into the blockchain because one of them invalidates the other. But the question is which of those came first? Because if the blockchain decides that the first transaction came first, then the second one doesn't process. And if the blockchain decides that the second transaction came first, then the first one doesn't process. That's basically the whole reason why we need a blockchain and why we need things like proof of work. In Namecoin, it's the exact same thing. If you register circle.com and then someone else or circle.bit, then someone else registers circle.bit. If you registered first, then you have the domain and they don't. If they register in Circle first, then they have the domain and you don't. So in both cases, you need the blockchain in order to allow the whole network to come to a consensus on what the order is. So what are some of the problems with Namecoin? Well, one of its benefits are that it's impossible to censor domain names. So there's no organization that can shut a domain down. It's a huge advantage, but at the same time, it actually is problematic. So one of the issues is that if, for example, I register some domain, and then some squatter comes in and registers a whole bunch of misspellings around it. So say I register ethereum.bit, but someone else registers etheruem.bit or etherium.bit or etheruem.bit and so forth. And they can sort of surround my domain and either grab a whole bunch of advertising revenue from that or even put various different kinds of scam sites on there. So with a centralized domain name system, we have a way of solving that. The internet has a governance mechanism that allows you to get those domains back under certain circumstances. Decentralized domain name systems don't have that option. So that's one problem. Another problem is the issue of pricing. So how much should a domain cost? If a domain costs $10,000, then what happens is that nobody can get a domain. If a domain costs 1 cent, then what happens is that squatters buy up all the domains and resell them at what the actual fair price is. So in general, we seem to have come to a consensus that a domain should cost somewhere around $8 or $10. Now, so the problem is that centralized systems can maintain that kind of stable price level. It's entirely unclear how a decentralized system could come together and determine what the optimal price is. Now, in general, the problem of figuring out what the optimal price of an asset is solved by markets. It's solved by basically supply and demand. We have a hugely liquid market where there's some people want to buy and some people want to sell, and that figures out what the optimal price is. The reason why that doesn't work with domains is basically that domains are very much non-fungible. So currency Bitcoin is the ultimate fungible asset. This Bitcoin is worth the same as that Bitcoin is worth the same as this other Bitcoin. Whereas with domains, they're typically non-fungible. Ethereum.bit and say Ethereum.bit might be worth like thousands of times more than something, say, Ethereum.bit with a Q at the front. Circle.bit is worth a lot more than Circle.bit. And so you can potentially make various different heuristics in order to figure out how expensive or how cheap a certain domain is going to be. But ultimately, there's a lot of domains that are just unique, and it's very hard to make any kind of liquid market to actually figure out how much each one should cost. The best you can do is probably some kind of machine learning algorithm, and if you encode the machine learning algorithm open source into a network, then you're running the risk of the whole system becoming gameable. So, but is Namecoin worthless? Absolutely not. So there are definitely a lot of applications where Namecoin can be used. So one example is distributed messaging applications. So the concept of distributed messaging applications has become very popular lately. You have a whole bunch of sort of private messengers, things like Pigeon, Jibberbot. Then you also have BitMessage. So with all these different protocols, what the problem is that in any of these messaging protocols, you have to have some kind of ID. You have to have some way of identifying users. So far there's two solutions. One solution is to just rely on a centralized identifier. So even if I'm using a theoretically decentralized messaging protocol like XMPP, fundamentally, my name on that would have to be, something at gmail.com or something at some other provider.com. This is Bitcoin. This is supposed to be a decentralized architecture here. Why do you need providers? On the other extreme, though, you have BitMessage. So BitMessage is decentralized. You don't have providers. But the problem there is your ID is this big, long, garbled 34-character string. It's basically exactly like a Bitcoin address. Now, why does it have to be that way? Why can't anyone have any name, register any name they want on BitMessage? Or why can't anyone set up any accounts with whatever they want on BitMessage? The problem is, well, what if I want the name George? Then it would be easy for me to create an account with the name George. But then you would also be able to create an account with the name George. There would be no way of figuring out who deserves to have that name. Once again, that's a problem of which one came first. Need a blockchain to solve it. Namecoin can do it. I can easily see a world where in 2 or 3 years, all of these sort of distributed messaging protocols rely on something like Namecoin as a backend. There already is a service called onename.io that's moving in this direction, basically tying your public key and some other information to a Namecoin address. I think we're going to see a lot more of this stuff as time goes on. So, next one came along in Ripple. So this concept is actually slightly older than Bitcoin. It was originally invented by Ryan Kruger in 2004. So idea here is that Ripple tries to create a monetary system that's essentially based on the relationships that already exist between people. So in sociology, there's this concept of 6 degrees of separation, where between any 2 people in the world, you can theoretically, it should be possible to find a link, or a chain of 6 links, such that I know person A knows person B knows C knows D knows E, and E finally knows U. And so the idea here is to try and leverage that sort of interconnectedness into a monetary system. So here's how that works. Suppose you have the social graph of people, where everyone has friends and acquaintances, and they all trust each other with a credit line to some certain extent. So in this case, say $5. Now, let's say in our current state, A owes $3 to B and B owes $5 to C. Now we say, oh, what if D wants to transfer $5 to A? Well, they don't know each other, they don't have a credit line. So what happens is, the system in the background finds the shortest path. And so the $5 transfer sort of ripples through the entire pathway. D starts to owe $5 to C, then C would end up transferring $5 to B, but what that means is that B's debt to C gets canceled out. Then A had a debt of $3 to B, and then that gets turned into a debt of $2 from B to A. And then so what happens at the end? Well, C goes from plus $5 from D to plus $5 from B to plus $5 from D, so C stays the same. B goes from plus 3 from A and minus 5 to C so -2 to just -2 going to A, and A goes from -3 to plus 2. So that's exactly what you wanted to do. So in 2011, Jen McCaleb started working on Ripple, the company, which tries to take this idea and combines it with a distributed consensus architecture and really turn this into a mainstream payment system. Now, one of the problems that Ripple encountered is that in reality, they're not going to be able to get the entire world to sort of put their social connections into the system. So, ultimately, the usability problem of getting people to quantify how much they trust certain other people is not really something that people are used to. So, what they came up with is 2 things. First of all, they created a currency called XRP. So in the Ripple network, most transfers are done through this sort of debt transfer, but XRP is debt-free, it's trust-free. So if you want to make a transfer between two people who don't know each other, then you can just beam XRP between them. And then the second feature is they have this concept called gateways. So the idea here is to sort of do a centralized bootstrap. So we have exchanges that a lot of people trust. So Bitstamp, for example, is a Ripple gateway. And so Bitstamp basically, and what happens is that when you deposit $100 into Bitstamp trusts you, gives you a credit line to the extent of $100. And now you have sort of 100 Bitstamp dollars. And then if you want to transfer $100 to someone else, then the exact same sort of transfer happens. So your Bitstamp's debt to you might say reduce from $100 to $90, but then Bitstamp's debt to someone else would increase from say $0 to $10. So that's basically what Ripple, and the fun part about Ripple is that it supports multiple currencies, and so you can even do decentralized exchange. You can even say, you know, Bitstamp trusts me with $90 instead of $100, and Bitstamp trusts someone else with 17 euros instead of 10 euros. So you can easily convert between different currencies. That's actually pretty much the main application of Ripple right now. That basically as a Bitcoin exchange, as a sort of gateway between the trust-based world of fiat currencies and the banking system and the world of cryptocurrency. So the advantage is basically that Ripple theoretically allows you to store any currency on the blockchain if someone is willing to act as a trusted issuer. If you're willing to trust, if there's someone that you can trust to have a debt for you. So then in 2012, people started working on this concept of covered coins. So covered coins is basically say, oh, well, what we can do is we can actually track specific Bitcoins as having a particular color, and you trace them through the blockchain. So in general, for example, I might say, I'm a bank, or rather, let's say I'm a gold storing company. I have 5,000 ounces of gold. I am going to take these 5,000 satoshis, these 5,000 small units of Bitcoin, and I'm going to say each of these satoshis is worth 1 ounce of gold, and I'm willing to redeem it myself. Then people can track those specific satoshis through the blockchain, exactly like they would track any other Bitcoins, and you can trace them, you can trade them, and so you can trade them. So if there's a transaction whose inputs are all gold coins, then its outputs are also going to be gold coins, and then you would trade them exactly like normal Bitcoins, but their value would be actually backed by my gold. So what you show here is that you can even do transactions that have multiple different colors. So say it's sort of like a flowing water bottle. So you have a transaction with different outputs. So say you have 4 black coins at the top, 4 gray coins in the middle, 4 light gray coins at the bottom, and just sort of trace them going to the right. And so the benefit here is that what you have is what's called an atomic swap. So let's say, for example, that person A controls the private keys behind these outputs, person B controls these outputs, then person A controls these outputs at the bottom right, and person B controls these. So what happens here? What you have is, you have one transaction where simultaneously the black coins are going from A to B, and the gray coins and the light gray coins are going from B to A. So trust-free exchange. Theoretically, you don't need an exchange in order to trade. And potentially, this is just another way of solving the exchange problem. Now, the concept does have its flaws. So, for example, although it's possible to do atomic swaps, what you can't do is you can't have an atomic order book. So you can't place an order that says, I am willing to sell these. I'm willing to provide these black coins to these 5 black coins to anyone who's willing to provide you with 10 gray coins. The reason why you can't is basically the fact that the Bitcoin system itself is not color aware. So color is just an extra sort of semantic layer that we add on top of the blockchain. There's the concept of this transaction output is gray or this transaction output is black. That's not really something that the underlying Bitcoin protocol itself can understand. So if you make an order, there's no way to prevent someone from filling an order that you meant for, say, 10 black coin satoshis with just 10 regular satoshis that are almost worthless. So the pros of the approach, however, are that it's basically completely interoperable with Bitcoin. You don't need a separate blockchain, and you don't necessarily, and you can trade between Bitcoins and some colored assets directly. So with the traditional exchange architecture, let's say you want to convert US dollars to Bitcoins. Then what you need to do is, first, deposit those US dollars into Bitstamp, turn them into Bitstamp US dollars. Then on Bitstamp, you trade them for Bitstamp BTC. And then you withdraw Bitstamp BTC and you get normal BTC. On Ripple, you have normal US dollars, then you upload them and turn them into Bitstamp Ripple US dollars. Then on Ripple, you trade them for Bitstamp Ripple BTC. And then you convert them into actual BTC. Here it's actually simpler. What you do is you first of all take any kind normal USD, turn them into Bitstamp colored coin USD, and then you directly trade them for BTC. So why is this a big advantage? Actually, it's potentially very huge, and the reason is that if you look at all of the exchange failures in the past 3 years, all of the failures have had to do with the exchange losing their Bitcoins. There really haven't been that many failures in terms of exchanges losing their dollars. So if you can get rid of the step where the exchange holds your Bitcoins in reserve, then potentially you've made a massive improvement. Now, what I will say in favor of systems like Ripple is that it actually is possible to at least partially decentralize the gateway. You can have the gateway be basically an existing pool. So there are different ways of sort of incrementally improving upon the problem from all angles. Now there's also Mastercoin. So Mastercoin is similar to colored coins as an alternative on blockchain protocol. It's Mastercoin. It basically uses Bitcoin just purely as a data layer, and then it does various different kinds of on-blockchain transfers on top. So Mastercoin actually allows you to place orders. It allows you to do things like savings wallets with withdrawal limits. It allows you to do some basic financial contracts. It allows you to do on-blockchain gambling. So there's this list of about 30 different things that Mastercoin actually lets you do. And Mastercoin is capable of doing that because it's not really based on the underlying Bitcoin. So a Mastercoin is not a Bitcoin. A Bitcoin output with just 6,000 Satoshis could be a million Mastercoins. Mastercoin just uses the Bitcoin network as a data layer. So there's another pretty much equivalent protocol called Counterparty that lets you do a very similar thing. Now, what are the disadvantages of colored coins and Mastercoin? Big one is actually scalability, because the reason is that first of all, both of them are on the Bitcoin blockchain, and there's a lot of Bitcoin developers that are not particularly happy about the fact that these protocols are basically polluting the blockchain with data. So, for example, there was a spat in the forums recently between the Bitcoin developers and the counterparty developers, where the Bitcoin developers reduced the maximum number of bytes of data that you can put in a transaction output from 80 to 40, specifically with the intent of making protocols like counterparty more difficult. So the problem is obviously that the reason why the Bitcoin developers don't like them is because it introduces bloat into the blockchain. The Bitcoin blockchain is already 12 gigabytes, and so if you just dump all of the protocols onto the same chain, then you have a sort of storage issue. So that's but on the other hand, you do have this advantage that these protocols are directly interoperable with Bitcoin. So now here is where we come to Ethereum. So in 2013, what I was seeing is that there was actually, after colored coins and Mastercoin, there was actually dozens of all these next generation coins. And what they were doing is they were trying to tack on lots of features. So this was the era where there were a lot of buzzwords floating around. There were people talking about things like decentralized exchange, financial derivatives, bets, on-blockchain gambling, savings wallets, escrow contracts, and this whole laundry list of features that they wanted people to do, namecoin functionality, and so forth. And the problem is that and they were having all these protocols with all these 50 different things that you can do with them. So one of the issues that I see with this paradigm is that it's if you compare it to a computer, what you would really have is, just imagine if your computer actually had a separate hardware module for Internet Explorer, a separate hardware module for Solitaire, a separate hardware module for World of Warcraft, a separate hardware module for just about every program you would ever want to run. What would your computer look like? Well, it would cost about $6,000. It would have about 200 programs on it. You would not be able to download any program without paying $100 for a hardware module. maybe it might be a bit more viable to write proprietary software because it won't be so easy to pirate it. But that's it's not going to be a fun world. So fortunately, in the 1930s, we came up with this concept of a programming language, where instead of having a hardware module for each separate task, you had a hardware module to act as an interpreter for a programming language, and then in that language, you would write whatever applications you wanted. So you wanted an Internet Explorer, you actually write it in a programming language, which can then actually get compiled onto various different hardware architectures. So it's this really nice, well-designed, massively generalized solution that really solved the problem. In the internet, from 1990s, the internet was just HTML, and eventually we came up with this concept of HTML forms. So this is another analogy. HTML contains a lot of these distinct features, things like bold, underline. At some point, people wanted forms, so let's have a specific feature for forms. Fortunately, at some point around 2000, we actually invented a much better solution, which is JavaScript. Hey guys, if people want to do everything in the web browser, let's have a programming language that actually lets people do what they want. And whatever feature people want to add, they can just do it on top. The inventor of JavaScript never actually intended for people to write Gmail on top of JavaScript. He never intended people to write Facebook on top of JavaScript. He never intended for people to write Bitcoin wallets on top of JavaScript. And yet, because JavaScript is this Turing-complete programming language, which means that you can do any kind of computation on it that's mathematically possible, it becomes this platform for innovation, and people can just keep on building stuff on top for decades longer. If it worked for JavaScript, all these sort of client-side Bitcoin applications pretty much wouldn't exist. So, how does Ethereum work? So if we go back to the model of Bitcoin as a state machine, so there is a database and there is a transition function. Ethereum takes that abstraction and brings it to the maximum highest possible level. So essentially, in Ethereum, you're sort of allowed to encode whatever transition function you want. So the state contains accounts. Each account has an address. It has some balance of Ether. Ether is the internal currency in Ethereum, similar to the XRP in Ripple, or the master coin in the master protocol, or XCP in the counterparty. And it also has optionally, it has storage and code. And the idea is that a transaction has a sender, it has a receiver, it has an amount of Ether, and it has some value, or it has some data, and data can contain some values. And what is the process of applying a transaction onto a state? Well, first of all, this one, it clearly goes from this account to this account. So, and it's sending 10 Ether. So the first thing that you do is you subtract 10 Ether from here, and you add 10 Ether to the other account. Then, hey look, the receiving account has some code. And the code says, if the contract storage at the zero data value is not yet present, then set that value at the storage to the first item in the data. So okay, so data 0 is 2, so let's see. Contract storage 2, 0, 1, 2. Oh hey, it's not set yet. So let's set that value to Charlie. And there we go, Charlie. So what this is basically a namepoint contract. So it's a contract in Ethereum that implements namepoint in 2 lines of code. So back in January, the pitch for Ethereum was you can implement namepoint in 5 lines of code. Over the past 2 weeks, our lead developer and myself have been working on a bunch of protocol changes to Ethereum that actually lets you knock that down to 2 lines. Right. So you can do namepoint, and potentially you can, because it's a Turing-complete platform, you can literally do anything. So what can transactions do? So they execute contract code. Contract code can read and write state, and it can execute other transactions. So one important point here, a lot of people raise the point, well, okay, so the main benefit of Ethereum is that it has script. Well, Bitcoin has script too, so why do you need Ethereum? So the answer here is that Bitcoin script is actually very limited in a few very important ways. So a lot of people talk about Ethereum's Turing completeness. That's powerful. It's actually not even the most interesting part. So there's several different things. So first of all, in Bitcoin, Bitcoin is a system that's based on transaction outputs. So if you have a transaction output, then that transaction output state can only be one of 2 things. It can be spent or unspent. And if it's unspent, then there are certain rules in which it can be spent, and that's it. So this is actually one of the reasons why something like colored coins is hard. There's no way to encode this is a gold output into a colored coin output. So theoretically, you can obviously invent data that says this is gold, but there's no way there's no way in the protocol to enforce the fact that people can only put the statement this is gold if the transaction actually has gold coin inputs coming in. So basically, in order to figure out what color a given transaction output is in the colored coins protocol, you actually have to search your way all the way through the entire blockchain. That's one of the scalability issues that we talked about, or that I mentioned rather. So that's one advantage. That's one limitation of Bitcoin. There's no state. Another limitation is that these scripting language. First of all, the scripting language in Ethereum, it has this nice recursive functionality where if a transaction gets sent into a contract, then that contract can actually send other transactions. And so you can theoretically encode like pretty much almost any kind of other important point is that scripting language has some access to the blockchain data. So for example, one of the issues here in Bitcoin is that there's no good source of randomness if you want to say do some kind of gambling application. So with Ethereum, you could just use some values, like say for example the previous block hashes, and you get your source of randomness. So there's Turing completeness. There is the fact that it has this extended state. There's the randomness, and there's also this idea that contract code actually does stuff. So it's not just the system that says, it's just is this output spent or is this unspent. Accounts can have whatever state they want. So what does the Ethereum blockchain look like? Well, analogy is actually, if any of you have ever really looked into Git is the version control system. If you're a programmer, chances are you know what it is. So the blockchain is actually very similar. So when you have in each block, or as they're called commits in Git, when you have this first one, you have a set of changes, and then you have a tree, where the tree contains all of the state. So in Git, the state basically consists of all the files, and I believe the tree even goes further with the subfile, like parts of files. So in Ethereum, it's the same thing. So we have a tree, and that tree provides all of the account balances, and you have a transaction list. So the benefit of the architecture is that every single block actually contains the entire balance sheet. But also, that sounds like it's going to be expensive. That sounds like it might be expensive. In Bitcoin, the balance sheet is 500 megabytes, so you're going to have 500 megabytes per block. Well, no, you're not. And the reason is that actually, if there aren't any changes, then the tree actually ends up pointing to the same object. So in this case, for example, you see from this commit to this commit, the value of new.txt and the value of test.txt was never actually changed. So what happens is that this test.txt points to this object, and then the next block, the test.txt points to the exact same object. So even though both commits contain the entire tree, they're both actually most of the time pointing to the exact same data. It's optimal deduplication. So there's an entire part of computer science that's dedicated to this concept of functional data structures, and so we rely on this concept very heavily. So what is the potential of these technologies? So there's this idea of smart contracts. So a regular contract is, I agree to give you $300 if you perform some task. So in a consumer to merchant scenario, it's just a merchant sending a product to a consumer. It could be an employment contract. It really could be almost anything. So a smart contract is basically it's a self-enforcing contract. So I put $300 into a box for an Ethereum contract, or some crazy Bitcoin transaction output, which automatically sends the for $300 to you if you perform some particular task. So ideally, the task would even be cryptographically determinable. So one example here is, what if your hard drive is encrypted and you forgot the password, and you want the network to actually try and decode the password for you. So one approach is to hand it off to one particular person. Another approach is you can actually do the whole thing just literally over the cloud using smart contracts. You can come up with a smart contract that says, if you send in a transaction, containing a password which decrypts this block of the file into something which is intelligible, then the contract automatically sends you the $300. So that's other times, however, you do need what's basically judges to determine if a task has been fulfilled. So for example, in a consumer merchant environment, you need escrow. So this is one of the criticisms of Bitcoin, for example, is that there is no concept of consumer protection. So this criticism applies on two fronts. So it applies on the front that there is it applies on the front that from the consumer merchant standpoint, what if the merchant scams the consumer? The payment is irreversible, and also from the point of view of you storing your Bitcoins. If you store your Bitcoins yourself, then you could get hacked and you could lose all your Bitcoins. Just the fact that ownership of a private key by itself does not necessarily prove that you intend to send the money somewhere. On the other hand, if you decide to store your Bitcoins with a centralized service, then that centralized service could turn out to be Mt. Gox. So that's something that smart contracts can actually solve. So even in Bitcoin, there's this concept of multi-sig, where a single address can have 3 private keys. So in a consumer merchant environment, the way this works is, when I pay for a product, we create a multi-sig with 2 out of 3 between myself, a merchant, and some third-party arbitrator. Then the merchant sees that the money got there. The merchant sends the product. Then what I do is, when I receive the product, I would send a transaction, which sending from the multi-sig to the merchant, and I would sign the transaction. Then the transaction requires 2 out of 3. So I would sign the transaction, and then I would send it off to the merchant, and the merchant would provide the second signature, and the merchant would get the money. If the merchant decides not to send the product, then they can sign a transaction refunding me, and I can co-sign it. If the consumer and the merchant come to a disagreement, then the consumer says, I never received the product, the merchant says I sent it, then they can contact the arbitrator, and then the arbitrator can decide which party has the better case, and the arbitrator can sign a transaction with that person, and then send money off to them. In the consumer environment, there's also the exact same thing. So you have a wallet with 3 private keys. You control 2 of them. You put one key on your computer, you put 1 key in cold storage, and then the 3rd key is actually controlled by a central party. So the idea here is that you use 2-factor authentication. So with every transaction that you make from your account, you have to sign it with your private key on your local computer. You also have to take out your phone, and you have to use your magic Google Authenticator application in order to prove to the server that you're actually authorizing the transaction. So usually that's the way it works. What happens if you lose your private key? Then you go into cold storage, and you still have another private key. What happens if the central party disappears? Then you have 2 private keys. What happens if the central party turns out to be evil? Then they only have 1 private key, they can't take the money. So these are the kinds of things that Bitcoin offers, and in Ethereum you can potentially become a lot more, make these ideas a lot more powerful. You can have contracts that say, here is 5 private keys. You need 1 private key to authorize transfers of up to $100 a day. 3 private keys to authorize up to $2,000 a day, and 5 private keys to authorize anything else. So, and the ultimate thing is that with Ethereum is that everything is a contract. So Namecoin, we already talked about, name registration, 2 lines of code. Subcurrency. Once again, a currency is just a database with the rule that the only modification you're allowed to make is subtracting X units from here and adding X units to there. That's something you can put into a contract. Decentralized exchange, and put that into a contract as well. Hedging. So this is a good one. I put $1,000 worth of Ether into a contract. You put $1,000 worth of Ether into a contract. After 30 days, the contract automatically returns $1,000 worth of Ether to you and the rest to myself. So the idea there is that you can now have your money inside of the cryptocurrency ecosystem, and you can actually know that you're going to get the same amount of money in real value back. You're protected from all volatility, and the system does not rely on trusting any kind of issuers. Now, it does rely on trusting a data feeds, so entities that tell you what's the value of 1 Ether. But that's still a much lower level of trust. Theoretically, you can distribute it. You can have 10 or 20 different data feeds, and it's incredibly low infrastructure. It's also something that's available around the world. It's much cleaner from a regulatory standpoint. You're not necessarily even touching the traditional banking system, and you get the stability benefits of the dollar. Finally, this is what I get people get really excited about, decentralized Dropbox. So this is basically, if I have a 100 gigabyte file and I want the cloud to store it, what I can do is I can make a contract that says, every hour, send 1 unit, 1 ether, to whoever submits a cryptographic proof that they have the file. And that's something that the contract can enforce all by itself. It uses the mechanism called Oracle trees. And basically, in the contract, in this decentralized way, incentivizes the network to keep on storing your file. So on the consumer side, it's probably going to be much cheaper. Dropbox has a markup of about 100x. This could probably push the markup way down. And you also have as much backup as you want. If you want more people to back up your file, you just raise the price. And on the seller side, you can now earn money by renting out your hard drive. So there's obviously there's a lot of challenges still remaining in the cryptocurrency 2.0 world. We have not solved issues like monetary policy. How do we create a currency whose price is stable? So I did describe a hedging mechanism, and you can potentially turn that into something that behaves like a currency. But there's still a problem to determine how to exactly do it optimally. Is it possible to somehow put in identity into the blockchain, create a system that's one per person? Is it possible to solve the scalability issue? Bitcoin is one blockchain, Ethereum is one blockchain, every node has to process every transaction. Theoretically, we might be able to do better. There are various different architectures that might improve upon the problem in various different ways. Mining centralization, Bitcoin has ASICs. In Ethereum, we're looking at an innovative mining algorithm that actually uses the Ethereum VM's own Turing complete computation as part of the mining process. And so the argument there is that if you have an ASIC that can do Ethereum mining, then what you have is an ASIC that can interpret a Turing complete programming language. So an ASIC for arbitrary computation, which is called a CPU. So it's but the problem is still very far from solved. Useful proof of work. So the nice thing about all these different ideas is that cryptocurrency 2.0 is not just one currency, it's a platform for innovation. So there are all these different ideas of creating your own currency with different properties. Proof of excellence. Can you create a currency that automatically rewards working on research problems? It's it's the stuff you can build on top. So there's still lots of things to be done in the cryptocurrency world. There's a lot of these different advanced cryptographic protocols, things like SCIP. This is basically you write a program, and then you construct a cryptographic proof that you ran the program. This is potentially like the ultimate scalability solution. Code obfuscation. You can have proprietary contracts. You can have Ethereum contracts that store Bitcoin private keys and use them to sign transactions, but you can't actually get the private key out. This stuff is very early stage. It could come, but it'll take about 10 years to finish off. Basically, cryptocurrency 2.0 is about taking the world of cryptocurrency and bringing it to the next level. It's about taking some of the ideas around Bitcoin and using them to do more than just money. But ultimately, once again, there's still a really long way to go. All of the protocols that we have so far, Bitcoin, coins, Ripple, Ethereum, they all rely on elementary cryptography. Can we do even better? What is crypto? We now have many examples of cryptocurrency 2.0 protocols. What is cryptocurrency 3.0 going to look like? I think the future of cryptocurrency is going to be a very bright one. Yes. So proof of proof, this is this idea where basically you randomly generate so we have a blockchain which randomly generates mathematical theorems, and the idea is that although it's pretty much impossible to try and automatically computationally prove theorems. These days, all the interesting theorems are still proven with mathematicians by hand. And once a proof is made, you can actually have a computer verify the proof. So the idea here is that you can actually encode mathematical theorems into a blockchain, and you can have this completely decentralized trust-free mechanism that says whoever proves this theorem automatically gets 50,000 units of this currency. So it's Similar to how Prime Coin is supposed to incentivize research and scientific computation, you can have a currency that just automatically rewards people working on various different research problems. So the challenge is, how do you add new theorems dynamically into the problem? So one way is you can add theorems you can sort of randomly generate theorems, and most of them are going to get solved pretty quickly. But you can set up your algorithm so that the reward goes up over time. So if you have a theorem that gets solved in a few hours, chances are it's an easy one, there's a tiny reward. But if there's some theorem that gets generated and gets unsolved for a few years, that's going to rack up a huge reward, and people might get really interested in working on it. So it's basically this decentralized protocol for basically funding pretty much every math department in the world. Yes.
Ethereum succeeds fully integrating will it destroy Bitcoin as a currency?
I don't think so. Bitcoin is still a great store of value. I think Bitcoin has this idea of 21 million units, and so Ethereum we have a somewhat more inflationary model. And in general, Ethereum is not going to replace all of these. So, for example, something like Ripple, we're not even targeting the niche of interfacing with the banking system, trying to be an exchange between dollars and BTC. We're specifically targeting this concept of advanced applications, non-monetary applications, and smart contracts. So I think there's a space in the cryptocurrency world for at the very least several different protocols and lots of protocols on top of protocols. Yes.
Hey, Vitalik, thank you for coming from Canada, Jim Robinson. Open-ended question just about the whole thing of hedging. Could you just speak a little bit more about that? I personally really intrigued by that whole angle.
Okay, right. So
you kind of blew right through it. So.
Okay, here's how it works. Once again, so one of the big problems with Bitcoin is volatility. People are uncomfortable with accepting Bitcoin payments if their Bitcoin has some chance of dropping like 20% the next day. So what you do is, in Ethereum, you have this contract where I put in $1,000, so in Ethereum, Ether is the internal currency. I put in $1,000 worth of Ether. You put in $1,000 worth of Ether. Then 30 days later, you get $1,000 worth of Ether back, and I get the rest back. So idea there is that now the contract does have to get the data about the Ether price from some outside source, but if it does that, what you had is, as long as there's speculators willing to take the other side of the trade, so as long as there's speculators that are bullish on the value of Ether, you have this mechanism that allows you to still maintain $1,000 worth of value, regardless of what happens to Ether, without requiring any kind of issuers.
What kind of security issues do you think would arise if anybody in the network could cause any other peer to execute arbitrary script?
Right. So there's two problems here. One problem is obviously what happens if the script contains some kind of exploit. So the answer is that the Ethereum scripting language is actually, even though it's very powerful, it's also incredibly weak. The Ethereum scripts cannot access the internet. It cannot read your file system. There is absolutely no opcode that lets you do that. So that's the way in which we solve a lot of the security issues. Then there's a problem of, what if you write a contract that's an infinite loop? Can you force people to execute an infinite loop? So the answer there is we have computational fees that you have to pay there are transaction fees you have to pay per computational step. So if you have an infinite loop, eventually it's going to run out of gas, and you have to pay, you as the creator of that contract, or of that transaction, have to pay all of the fees anyway, and but the execution stops. Yeah. What do you mean? That's actually one of the problems that we're looking at this point. It's a mechanism that's going to have to be a lot more restrictive than Bitcoin, because Bitcoin's, I've wrote even an article on this on the Ethereum blog, Bitcoin's transaction fee system is way too lax in order to do some of this sort of heavy duty computation stuff. So we're looking at this sort of dynamic, somewhat mandatory fee sort of system.